Right now, as you sit there watching this video, you are moving at over 1,000 miles per hour. You don't feel it. You've never felt it. And that's the problem, because if Earth suddenly stopped spinning for just 5 seconds, what would happen to the oceans? What would happen to the atmosphere? And here's the part that's going to keep you watching. What would happen to you? If you're curious about the hidden forces shaping our world, forces you can't see, can't feel, but absolutely cannot survive without you're in the right place, consider subscribing. There's always another mystery waiting. Okay, let's set the stage. Earth rotates once every 23 hours and 56 minutes. At the equator, the surface is moving at roughly 1,040 miles per hour. That's faster than the speed of sound in a jet fighter. At full throttle, but you don't feel any of this. And the reason is beautifully simple. Everything around you, the air, the water, your coffee mug, your cat, it's all moving at the same speed, in the same direction. You're all passengers on the same ride. Now, physicists call this an inertial reference frame, but you can just call it the reason you're alive. Because here's what people don't often think about. Earth's rotation isn't just some fun cosmic fact. It is actively shaping the thickness of the atmosphere above your head, the direction of every ocean current, and the structural integrity of the planet itself. So what happens if you take that away? Not forever, not even for a minute. Just 5 seconds it sounds harmless. 5 seconds is nothing. You can hold your breath for 5 seconds. You can microwave something for 5 seconds, even though you know it needs 10, but 5 seconds without rotation. That's a completely different kind of nothing. Let's start the clock. Second one, the ground beneath your feet stops. Instantly. No warning, no gradual slowdown. The solid Earth, all 6 sextillion tons of it, just halts. But you don't stop. Neither does anything else that isn't bolted to bedrock. This is Newton's first law. An object in motion stays in motion unless acted upon by an external force. And right now, the only force that stopped was the one carrying the ground. You, the air, every building, every ocean. You're all still moving at the rotational speed of wherever you happen to be standing. At the equator, that means everything not anchored to the deep Earth is now flying sideways at 1,040 miles per hour. Let me put that in perspective. The strongest tornado ever recorded, the 1999 Bridge Creekmore tornado in Oklahoma, had wind speeds of about 302 miles per hour. What we're talking about is 3.5 times that. But here's the strange part. It's not just wind, it's everything. The air itself becomes a weapon. 1,000-mile-per-hour wind doesn't just blow things over, it disintegrates them. At those speeds, the friction between air molecules and solid surfaces generates enormous heat. Research on hypersonic aerodynamics, the kind NASA uses when designing spacecraft heat shields, tells us that objects moving through air at these velocities experience extreme thermal stress. Your house wouldn't blow away. It would be sandblasted into fragments, and some of those fragments would be on fire. Now, and this is important, the speed depends on your latitude. If you're standing at the equator, you're experiencing the full 1,040 miles per hour. But if you're at, say, 45 degrees latitude roughly, the latitude of Montreal or Milan, you're only moving at about 735 miles per hour. Still wildly fatal, but slightly less dramatic. And if you happen to be standing directly on the North or South Pole, you'd just spin in place for 5 seconds, and then stop. You'd be fine. Confused, maybe? Dizzy, definitely. But fine. That's already terrifying. But we're only 1 second in. Second 2, second 3, the winds are still raging. But now something much bigger is happening. The oceans. Water, like air, has inertia. And the world's oceans, containing roughly 332.5 million cubic miles of water. According to the USGS, we're all moving eastward with Earth's rotation. Now the basin has stopped, but the water hasn't. Imagine you're carrying a giant bowl of soup. You stop walking suddenly. What happens to the soup? Now scale that up to a planetary level. The result would be tsunamis that make every natural disaster in recorded history look gentle by comparison. Walls of water, potentially miles inland, sweeping across every coastline that faces east. We're not talking about storm surge. We're talking about the entire ocean lunging forward. Some estimates suggest the wave heights could reach several kilometers inland, depending on coastal geography. To be clear, precise numbers here are speculative. No one has run a peer-reviewed simulation of this exact scenario because, Well, it's never been a realistic concern. But the physics of fluid dynamics and inertial forces give us a reasonable framework to understand the scale. It would be beyond catastrophic. But here's the part that scientists find even more interesting than the tsunamis: the atmosphere. Air is lighter than water, so it responds even faster. The 1,000-mile-per-hour winds would scour the surface in the first second or two, but by second 3, something else is happening. The air is piling up. On one side of the planet, the side facing the direction of rotation, air molecules are slamming into the air that's been stopped by the ground's friction. It compresses, atmospheric pressure spikes in some areas and plummets in others. This is where things get theoretical, but leading atmospheric scientists suggest this pressure imbalance could create something unprecedented: a global-scale shock wave, not a sound wave, a shock wave. The kind of pressure discontinuity you see at the nose of a supersonic jet, but spanning continents. No human structure is built to withstand this. No mountain, no bunker, no beautifully engineered stick-figure house with reinforced walls. And the clock is still ticking. Something is happening beneath our feet. See, when we say Earth stopped spinning, we need to ask, what exactly stopped? Just the crust, the mantle too, all the way down to the core. Because Earth isn't a solid ball, it's layered. The outer core is liquid iron, churning and flowing. The mantle is semi-solid, moving over geological timescales. These layers rotate at very slightly different rates from the crust, a phenomenon called differential rotation, which is well documented in seismological research. If the crust stopped, but the mantle and core kept their angular momentum, even briefly, the shearing forces at the boundary between these layers would be staggering. The best analogy: imagine spinning a raw egg on a table and then stopping it with your finger for a moment. You let go and it starts spinning again, because the liquid inside never stopped. Now apply that to Earth. You've stopped the crust, but the liquid outer core. Generating Earth's magnetic field through what's called the geodynamo mechanism is still sloshing. For 5 seconds, the coupling between the core's motion and the crust's stability is disrupted. What does this mean? Honestly, we don't know with certainty. This is firmly in the realm of plausible hypothesis, not proven fact. But some geophysicists have speculated that even a brief decoupling could trigger massive seismic events. Not just earthquakes. We're talking about tectonic scale fracturing. The crust itself might crack in places. And volcanoes, magma chambers that were stable under the normal stress regime, could suddenly find their structural constraints rearranged. 5 seconds might be enough to trigger eruptions in systems that were already close to their tipping point. But here's where it gets really strange. Second 5, the last second, Earth starts spinning again. And in many ways, this is worse. The sudden reacceleration means everything gets hit twice. Once when the planet stopped, and once when it started back up. The oceans, which had already surged forward, now slosh backward. The atmosphere whipped. The crust, already stressed from 5 seconds of abnormal forces, is now jerked back into motion. This is like a planetary-scale car crash. And the car just got rear-ended 5 seconds after the first impact. Now, let's step back and ask something that nobody seems to talk about. Why does Earth spin at all? This isn't a trivial question. And the answer takes us back 4.5 billion years, to a disk of gas and dust swirling around a young sun. As particles in that disk collided and clumped together, they carried angular momentum, a fundamental property of physics that says spinning things tend to keep spinning. Unless something stops them, Earth inherited its rotation from the very process that built it. Every rock, every grain of dust that smashed into the growing proto-Earth added a little more spin. The giant impact that likely formed the Moon, a Mars-sized body called Deus, slamming into early Earth, probably set our current rotation rate. And here's a fact that might change how you see the world. Earth is actually slowing down. Right now, measurably tidal interactions with the Moon are gradually bleeding away our rotational energy. Every century, the day gets about 2.3 milliseconds longer. This is well established through studies of ancient coral growth rings and historical eclipse records. 600 million years ago, a day on Earth was only about 21 hours long. Someday, billions of years from now, Earth and the Moon will become tidally locked, and the planet will stop rotating relative to the Moon altogether. Earth will, in a sense, stop spinning on its own. But it'll take billions of years, not 5 seconds. And that makes all the difference. So here's what this thought experiment really teaches us. We live on a machine, a giant, spinning, layered, magnetically shielded, atmospherically balanced machine. And every single part of it, the spin rate, the core dynamics, the atmospheric circulation, the ocean currents, is connected, one thread, even for 5 seconds. And the whole tapestry unravels. The Coriolis effect, driven by rotation, steers hurricanes and trade winds. Without it, global weather patterns would be unrecognizable. Ocean circulation, including the thermaline conveyor that regulates Europe's climate, depends on Earth's spin. Even the shape of the planet, slightly bulging at the equator, is a product of centrifugal force from rotation. Stop the spin, and Earth would eventually settle into a more perfect sphere. The redistribution of ocean water alone could redraw every coastline on the planet. Everything you take for granted, the length of a day, the direction of the wind, the shape of your continent, exists because a cloud of dust started spinning 4.5 billion years ago and never stopped. 5 seconds of stillness would be enough to remind us, violently, catastrophically, that we're not standing on solid ground. We're riding a spinning rock through space, held together by momentum and physics. And the only reason it feels calm is because it has never, ever stopped. There's a strange comfort in that, though, because right now, at this exact moment, the system is working. The Earth is spinning. The atmosphere is holding. The magnetic field is shielding you from solar radiation. And you don't feel any of it. The most powerful forces keeping you alive are the ones you'll never notice. So the next time you're standing still, really still, in a quiet moment, maybe late at night, maybe just before sleep, remember this: you are never still. You're moving over 1,000 miles per hour. On a planet orbiting the sun at 67,000 miles per hour. In a solar system spiraling through a galaxy at nearly 500,000 miles per hour. And the only reason it feels like peace is because nothing has stopped yet. If you enjoyed exploring this mystery with us, subscribe to Exploratics. There are countless fascinating stories still waiting to be uncovered. Until next time, stay curious.